Hello students. So our today's topic is couple circuits. Basically we require couple circuit because whenever we do some numerical on theorems, if a inductor comes in between and it has got a coupling with some another inductor, then the equations using your mesh equations or the nodal equations gets changed because of the mutual inductance coefficient present between the two. So let's learn that what is this mutual inductance coefficient and what do we mean by the coupled circuits. So basically, if we go for the definition, you can just see from here that if we have got one circuit that is energized and another circuit that is not energized, but the energy gets transferred to this circuit by coupling, is called as coupled circuit. You can very well learn from this given circuit that I just drew that such type of circuit you already have studied, and that is your transformer. So even if we call for your transistor, it also comes in this category, but then we call for your another type of category of coupled circuits, that is your conductively coupled circuits. So when we talk about your conductively coupled circuits, we talk about the mutual impedance. We don't talk about the mutual inductance, but we talk about the mutual impedance here. And if you all remember that when we did our Z parameters, we calculated Z12 and Z21. So basically, mutual impedance is only this thing. If you are given with some numerical that we will just do, Z12 or Z21 will be called your mutual impedance. And if you are told to calculate it, you need to calculate this only. So the second category of your conductively coupled circuits are the inductively coupled circuits, which are also called magnetically coupled circuits, whose example we just discussed was your transformers. So we are going to come on to this topic a little bit later. So let's first do the numerical based on your conductively coupled circuits. So let's say that you people are given with a circuit like this is 2, a pi circuit has been given to you. So this is 3 ohms, this is 2 ohms, this is 5 ohm. It is the same as we did in our Z parameter. So this is your V1, I1, V2, and this is your I2. And now the question tells you to calculate your mutual impedance of this conductively coupled circuit. So whenever this thing will be asked to you, you can either calculate your Z12 or you can calculate your Z21, right? So let's calculate Z21 here. Let's first define it. It will be equal to V2 upon I1 for I2 equals to 0. So that means when my I2, these terminals are open, so that means I only need to go for the voltage drop across 3 ohms resistor. Let's say the current passing through 3 ohms is Ix here, because I need to calculate which part of this I1 is coming here. So now just see that there are two paths only because this path is open, so nothing is going to go there. So that makes 2 and 3 to be in series, right? So when I need to calculate my this Ix, so that means my this I1 is going to get divided half between 5 ohm and 5 ohm because both are in parallel. This is my I1. So this makes it to be this as 5 ohm and this as well as 3 plus 2, 5 ohms. So I1 will get divided into half. So this makes it to be, sorry. So here it will be I1 by 2. And here I am going to put the value. So this will become 3 by 2 I1. So I'm going to put the value here. So this will give me 3 by 2 I1 divided by I1 This cancels out and the value will be 3/2 ohms. So only this you have to do for conductively coupled circuits. So now we come on to your mutual inductance and the magnetically coupled circuits. So now we come on to the definition of our self-inductance. We all know that the voltage across the inductor is equal to self-inductance multiplied by rate of change of current through that inductor. So when we talk about inductor, it always comes in our mind that it has got a pair of terminal and it is a coil. So, but when we talk about mutual inductance does not physically present. Mutual inductor is not physically present. It is the property with which more than two coils are associated. Mutual inductance is a property with which two or more coils are coupled with one another. So let's discuss about the mutual inductance. But you have to just focus on this formula because from here we are going to derive the formula of your mutual inductance as well. So now let's discuss about the mutual inductance. Let's say that we have got this circuit in which our this coil L1 is supplied with a voltage V1 and a current is flowing that is changing with respect to time as I1. So that means the voltage across our L1 will be L1 di1 by dt. But now what will happen? There will be a flux that will get associated with the other flux that is lying in proximity with L1. So the voltage that will be developed, as we have not applied any voltage to our this coil, so there will still be a voltage that will get developed across it, and that can be defined by the mutual inductance coefficient M that will depend. Now V2, that is the voltage of this coil, will depend upon the current that is flowing in our first coil. You need to check this, that we are talking about voltage of this coil and that is being dependent upon the current in the first one, which was provided with the voltage. Now let's switch over to case number 2. So now we have provided V2 voltage to our this L2 coil and we are not supplying any voltage to L1 coil. Now what will happen? Again, because as the current is flowing through this L2 coil, so a flux will start evolving and that is going to link our this L1 coil, and now there will be a voltage that will get developed across L1 and this voltage will be equal to M, that is the mutual inductance coefficient between the two, multiplied by the rate of change of current in the other coil. So mind it, whenever we are going to define voltage with respect to mutual inductance coefficient, the current is always taken care of the that flowing in the other coil. Voltage of one will have current of the other coil. Similarly here, voltage of one will current of the other coil. So this you all should keep in mind. So while we talk about the self-inductance, it is always taken as positive. But when we talk about the voltage developed because of mutual inductance, that is M di by dt, it can be positive as well as negative. And how to decide that this voltage because of the mutual inductance will be positive or negative is decided by a convention that is known as dot convention. Basically, what is this dot convention is, there is a dot present whenever we get an inductor, there is a dot present. So depending on that how we are coupling the other coil in proximity to our this coil, along with that dot condition, the voltage that will be developed because of the mutual inductance can be positive or negative. So let's just take 4 cases from which it will be clear to you that what is this dot convention. The dot convention says that if the current enters or leaves at the dots, here you can see the current in our this L1 coil as well as L2 coil. It is entering at the dotted point. So that indicates that the voltage that will be developed here will be taken as positive. So here the voltage that will be developed will be plus MD. It can be I1 or I2 by dt. It will be positive in both the cases. So now let's come on to our second case. Here just see that the current is entering at the dotted point in coil number 1, but it is leaving at dotted point because the current is entering from this side and it is leaving from this point. So it is the opposite case. So that means in such conditions, the voltage developed because of the mutual inductance will be taken negative. So again, if we are talking about voltage in the first coil, it will be negative M di2 by dt, and for the voltage developed here, it will be negative of M di1 by dt. So it will be negative in both the cases. So now we come on to our case number C. Here you can see that the current again is leaving our coil number 1 and it is entering our coil number 2. So again, the voltage that will be developed here because of the mutual inductance will be taken negative for both the cases, right? So now we come on to our last thing. You can see that I1 is entering here and leaving at the dotted point. Similarly, I2 is entering here and leaving at the dotted point. So that means in both the cases, the current is leaving at the dot point. So in such case, again, the mutual inductance voltage will be positive in both the cases. So from here, you can just summarize that if the current is entering or leaving the coils at the dotted notation, then the mutual inductance will always be taken in positive value. While if the current is entering at one dot and leaving at the other, like in B and C cases, then it will always be taken as negative. Kindly note this down because this will be used for further writing the loop equations or the other values. So let's do a numerical based on this. So here we have to calculate the effective inductance of our this circuit. So let's say that the current flowing here is I. So we are going to consider a single inductor at a time along with the mutual inductance coefficient. And mind it here that there is a mutual inductance coefficient between 1 and 2 and 2 and 3 only. And there is no mutual inductance between 1 and 3 number coil, right? So you shouldn't get confused or there is no missing value here. So just let's write down the values. So the total voltage, we are going to start with our first coil. It will be equals to the self-inductance, that is 8 di by dt. Now mind one thing, that now the current is in series, so it will remain same in all of them. So there is no I1 or I2 current, so you shouldn't get confused. You should only concentrate on the positive or negative value of the mutual inductance. Now just see here that the current is leaving at the dot, but for the 2 number inductor, the current is entering at the dot. So that means my this value of mutual inductance 4 will be taken as negative. So this is my first set. Now I come on to my second one. So here it will be your plus, because I told you that the voltage because of self-inductance is always positive. So it will be plus 10 di by dt. So now as this 4 has got the negative sign, so it will remain negative here also. So now it is attached with this also. Now we have to check the mutual inductance polarity for this. So the current is entering at the dot and the current is also entering at the dot here. So that means our this 5 will be positive di by dt. So now we come on to the last one. So it will be plus 6 di by dt. And as we know that our this mutual inductance is positive, so now this will be this thing. Now we have to add and subtract all of them. So this gives me the value of di by dt I'm taking out. So this gives me the value of 34 minus 8. That gives me 26 di by dt. That gives me the self-inductance, efficient self-inductance as 26 henries. So this is how you give the polarity to the mutual inductance. So now let's come on to the coefficient of coupling between two inductors. So now we come on to the coefficient of coupling, that is given as K equals to mutual inductance between the two coils L1 and L2 divided by under root of L1 and L2. So if you people are given with the value of M, L1 and L2, you can calculate the value of this K. Now, basically, what is the coefficient of coupling? As I discussed before also, that if there is one coil and another coil is placed here, let's say the first one is energized and another one is placed here. So now it will depend upon the coefficient of coupling K, that how well the flux is getting induced in the second coil that is not energized. So for that, it is air coupling between them, or it can be iron core coupling. That is, a iron core is placed between the two coils for better coupling between them. The maximum value of K can be 1 for best coupling between any two coils, and that is sometimes in case of the iron core, but the maximum value that can be attained is 0.9 here. And when we talk about the air coupling between the two coils, the value between them varies from 0.4 to 0.8. So let's solve a numerical based on our coefficient of coupling. So you have got the numerical based on the coefficient of coupling as two inductively coupled coils have self-inductance of 50 millihenry and 200 millihenries, and K is given to you. You have to find the value of M. We have just done the formula that K equals to M divided by under root of L1, L2. So now just see that you have got the value of K, you have got the value of L1 as well as L2. So you need to calculate the value of M. So from here, you can just write down that your this K's value is 0.5 multiplied by under root of L1 is 50 into 10 raised to power minus 3, milli stands for minus 3, multiplied by 200 into 10 raised to power minus 3, the whole under root, will provide you with the value of mutual inductance M. So that comes out to be 50 millihenries. So now you come on to your second part that says that what is the maximum possible value of M. So for that purpose, you need to take the value of K as 1, because I already told you that the maximum attainable value of the coefficient coupling is 1. So taking K equals to 1 and putting the value here again. So again, you have to go for your under root L1, L2 here. So here you can just see that the value will come here to be 100 millihenries when you are going to solve the value with under root of L1 and L2. So this is how you do the numericals based on your coefficient of coupling. So now we come on to when there are three coils that are inductively coupled. So for such type, we define a inductance matrix in which the self-inductance is defined as the diagonal elements. Sorry, here it will be L22. And this will be L33. So when we talk about L12, L12 will be equal to L21, while L13 will be equal to L31. So here just see that these diagonal elements represent the self-inductance. L11 stands for L1 only, L22 stands for L2 only, and L33 stands for L3 only here. This is the self-inductance of these coils. So now basically the mutual inductance is given when the subscript is different. So that means L21 and L12 is the mutual inductance between coil number 1 and coil number 2. Similarly, L13 and L31 both will be equal, and they are the mutual inductance between coil number 1 and coil number 3. And similarly, L32 will be equal to L23, and that will be the mutual inductance between coil number 2 and coil number 3. So this is how we define our self-inductance, inductance matrix, sorry. So now let's do a small numerical based on this. So the numerical can come like that: the inductance matrix has been given. There are 3 coils and you have to find the inductances and indicate the dots for all the coils. So firstly, remember that these are the self inductances of the 3 coils. So that means this will be 4 Henries, this will be 2 Henries, and this will be 6 Henries. Now come on to the mutual inductance coefficient between coil number 1 and 2. So that means between 1 and 2, the mutual inductance coefficient is negative, right? So let's say if the current is entering here, so that means it will be leaving here, right? So that means that the mutual inductance coefficient between the two will be 4 Henries. Now you come on to 1 and 3. So the 1 and 3 is positive. So that means that if the current is entering at this dot, so that means the current is also entering the third coil at the dot. So that means the mutual inductance coefficient between the two 1 and 3 coil will be 1 Henries. And lastly, we come on to the mutual inductance coefficient between 2 and 3. As it is leaving here and it is entering at this, so that means the negative sign is there. We need to only mention that the mutual inductance coefficient between the two is 3 Henries. So this is how you perform it. You have to indicate all the inductances, whether it is mutual inductance or whatever it is, and you will be given the inductance matrix. So lastly, I will come on to your mesh equations as we did for your theorems when we discussed about the introduction of nodal analysis and mesh analysis. So basically, you will be given a circuit like this and you will be asked to write the mesh equations. So just storm your mind that can you write the mesh equations when there is a mutual inductance coefficient present here. So it's a homework for you that you all should write the equations, and that we are going to discuss in our next lecture, and you can check that you have correctly written them or not. So that's all for now. Thank you so much for watching.